All right, everybody, welcome to Unit 4, Notes 1. Buckle up for some longer notes. Grab a beverage, grab a snack. I'm working on a key lime LaCroix. If you've not had one, they're delightful. You can really taste the key. It sounds silly, but if you've never had one, give them a shot. Also, I apologize. You might need to turn up the volume. I'm sorry if this is quiet, but young Theodore is asleep, and if I wake him, then you probably won't have a video to be able to view tomorrow. So I've got to be a little on the quiet side here. So anyway, we're starting Unit 4. It's a pretty short unit. You'll notice it's just 2 sets of notes and a review. But we're talking about some functions. So hopefully you found that either tomorrow or yesterday, whenever you took or are taking your test, you're functioning well. Hello. And let's start with a little bit of review from Algebra 1. So a relation is any set of ordered pairs. The set of first coordinates in the ordered pair is the domain of the relation, and the set of second coordinates is the range of the relation. So the domain thing to remember, if you will, is that your domain are your x's and your range are your y's. So if we were listing the domain of the relation above, right? So we do some fancy, those are called butterfly brackets. Okay, and we would just list our x values in order from least to greatest, okay? In order from least to greatest. And if you're wondering, I am going to be a stickler on some of these things. That's not to be a jerk, but this is when we're really going to get used to seeing set notation and certain ways of writing things. There's not a lot to this chapter mathematically, so I want to make sure that the way we're writing things and the way we're talking about things is really on point. So yes, I am going to be a stickler about stuff like that. So please use the fancy butterfly brackets and do make sure that things are least to greatest. So our smallest x value here would be 0, followed by 1. Then we have 4. If you have repeated values, yes, you've got 4 twice. You do not need to list it twice. In fact, you should not list it twice. It should just be there once. So 0, 1, 4. We don't list it twice. Next is 9, and then 16. Okay, so that would be our domain. Those are our x values. The range of the relation. Well, again, same idea. You're listing your y values from least to greatest. So our smallest y value would be -4, followed by -2, then 0, 1, 2, and 3. Okay, and that's what's called a relation. Okay, now a function, which is what we're really talking about here, is a special kind of relation. Okay, it's a correspondence between two sets, a domain and a range, that assigns each member of D exactly one member of R. Okay, in other words, each element of the domain is mapped to one and only one element of the range. That means each input, right, which is your x value, has exactly one output or y value. So a function is a special type of relation where every input goes to only one output. Every x value goes to only one y value. So we want to take a look at these and determine, are they functions? Okay, so we've got the ordered pairs 1, 2, 2, 4, 3, 5, 2, 6, and 1, -3. And what you want to look for are repeated inputs, repeated x values, right? So I actually see 2 here. I've got 2 1s and 2 2s. So you really only need one of these to have this not work the way you want. But notice 1 has both the output 2 and -3. 2 has both the output 4 and 6. Either way you cut it, what that means is the input 1 and the input 2, both of those have more than one output. So this is not a function. Not a function. Okay, not what we're looking for here. Now, on the other side of things, now look, if you look through your inputs on B, right, you've got 1, 2, 3, 4, 5. Nothing's repeated, right? So each input, there's no opportunity to have an input that goes to an alternative output because each one only has one option, right? So this is indeed a function. Okay, so that's how you can tell if something's a function based on a list of ordered pairs, right? You just look to see if you have more than one output for any given input, okay? If you're asked to determine this graphically, if you're asked to determine this graphically, not to get too graphic with you here, but you're going to do what's called the vertical line test. So you want to ask yourself, okay, at any point in my graph, can I draw a vertical line through my graph and will it hit more than one point, right? If it doesn't, right, notice on this one, there's no place I can draw a line where it's going to hit more than one point, which means this is a function, right? It is a function, right? Because for any given x value, as you move from left to right, each one of those only has one y value. Same thing here, same idea. This is also a function. Now, when we get to this last one, you'll see, right, if we draw a vertical line here at 1, right, notice it hits this circle in 2 different points. Okay, it hits the circle in 2 different points. And the idea is, well, both of those would have, well, we won't estimate it here. It's going to be 2 point something. Both would have the x value of 1 and 2 point something, or 1 and negative 2 point, whatever that is, 2.9 something probably. And the idea is, well, you've got the same input 1, and one goes to 2 point something, the other one goes to negative 2 point something. Well, they go to 2 different outputs, so therefore this is not a function, and that's why the vertical line test works. So if you can draw a vertical line anywhere on there and it hits in more than one spot, that is how you know it is not a function. Okay? We also have this lovely thing called function notation, right? So the values of a function are the members of a range, right? So that's the values, the range, the outputs. These are all different words, different ways of saying the same thing, right? But to indicate the values of a function, you use function notation and write f parentheses x, right? F parentheses x denotes the value of f at x. This is usually shortened to f of x. So you'll hear me say a lot this unit and moving forward, f of x. Or in this case, if we look at a, we would say that f of 2. You're saying what is the value? See, what is the value of the function f at 2, right? Meaning, if you plug in 2 for x, what do you get, right? So let's take a look at how these work here. If you have f of 2, that's saying in your f function, just like I said, you're replacing your x's. It's telling you plug in 2 for x in your f function. So f of 2, I know this looks like f times 2. Don't overthink this here. This is what's called function notation. I'm not multiplying by 2 or anything like that. It's just a new notation, and hopefully it's actually not new. It's reviewed from last year. But all that's telling you is in your f function, plug in 2 for x. This is 2 times 2 instead of x minus 1. Okay, and then you just follow the order of operations. So f of 2 then, well, that would be 2 times 2 is 4 minus 1. So f of 2 is 3. Okay, another way to think about this is your x value, this is your y value. So depending on how I ask you for the answer, right, you could also write this as an ordered pair. This would be the ordered pair 2, 3, right, in your function. Okay, generally speaking, this is how I ask for it, but just to make sure we're all on the same page here in terms of what this means, whatever you plug in for x is your x value, and whatever it simplifies to once you plug it in is your y value. Okay, so let's take a look at another one here, g of negative 2. Well, that's telling you to plug negative 2 in for x in your g function. Okay, so g of negative 2, well, that's going to be negative 2 squared plus 1, right? Our g function is x squared plus 1, so we plug in negative 2. And now let's simplify. Exponents come first, so negative 2 squared. Notice the negative 2 is in parentheses, so I am squaring the whole negative 2. So this is a positive 4 plus 1, which means that g of negative 2, as I wrap up the order of operations, is 5. Very nice, very nice. Moving on to C, this one's a little bit more complicated, but it's the same idea. If A was telling you to plug in 2 every time you see an x, this is telling you to plug in a plus b every time you see an x. So f of a plus b is going to be 2 times, instead of x, a plus b minus 1. Okay, and then as we simplify that, the first thing, a plus b, the first thing we want to do is distribute, so 2a plus 2b minus 1. And if you notice, none of these are like terms, right? 2a is different from 2b is different from negative 1, so that's actually your final answer. Let me circle my one over here as well. And those are your answers, right? So if you have f of something or g of something, right, this function notation, it's essentially telling you to plug in a certain number for x. Okay, and it's that simple. Don't overthink it and think you're multiplying anything. It's nothing like that. Okay, So now we're getting to the point where we get to why these notes are so long, okay? So let's read through this real quick. It says a function family is a set of functions whose equations have a similar form. So for example, you'll see a bunch of examples here in a second, but linear functions, right? All linear functions have a graph that comes out as a line. Now those lines can look slightly different, but at the end of the day, they all create a line, okay? A parent function is the simplest function of a family of functions that preserves the definition or shape of the entire family. So it's the most basic form of that graph that you can get. We're going to spend some time learning about the basic function families and their parent functions. A function, we're going to talk about this a little bit, but a function is increasing if as x increases, meaning you're reading your graph from left to right, y also increases, and vice versa. As x, it's decreasing if as x increases. So again, you're reading it from left to right, y is decreasing, right? So the key for increasing and decreasing is to read your graph from left to right. And you're telling me is your graph going up or down in that scenario. So a function is constant if as x increases, y stays the same. Functions can be increasing, decreasing, or constant over different intervals, or they can be strictly increasing, decreasing, or constant. So we'll see a couple of those here in a moment. Functions may have maximum and minimum values, which are the highest and lowest values of the function. We won't worry about relative versus absolute maximums or minimums or anything like that yet. And then the x and y intercepts are found by substituting 0 in for x or y into the function rule. So we're going to take a look at a few of those things here and a bunch of different functions. So this is why I said, please, oh please, come and grab these, because if you're trying to copy all this down onto a separate sheet of paper, you're like, Mr. Kaplan, you are the absolute worst right now, because I don't want to copy all these parent functions down. And to which I say, well, that's a parent, you know what I'm saying, right? But that's why I told you to come get them. So if you didn't, sorry about you, you're out of luck, and here we go. So most of this we're not going to take too close of a look at, right? But the main idea here is, it feels like a lot of content, but the main goal from this is I want you to be familiar with these, right? I want you to be familiar. I'm not going to test you a ton over linear functions or anything like that. I'm not going to test you a ton over absolute value functions or quadratics, but the goal is in a couple months, when we're talking about quadratic functions, I don't want you to sit there and say, Mr. Kaplan, I've never ever in my life heard you say the word quadratic, okay? Right? The goal is familiarity here. I want you to understand that a quadratic is a type of function. I want you to understand that it creates a parabola, so on and so forth. I want you to know some of the basic features of these and be familiar with the name quadratic in reference to this shape here, which is a parabola. Okay, so that's all we're really going for here. So we're going to fill out some of this basic information, some of these characteristics to get accustomed with these ideas. And we're going to take a look at what these parent functions are. So the parent function for a line is f of x equals x. Whenever you see an f of x, right, you've oftentimes seen this more as y equals x. F of x is just this new function notation. F of x is a fancy way of saying y. Here's a table of values, right? If you were to plug in x, what do you get for your y? And now let's really examine these here. Let's look at the domain, range, increasing, decreasing, maximum, minimum. So if we look at the graph to the right here, the domain and range, well, I know we don't have arrows necessarily, but a line goes on and on forever in both directions, right? So your domain of this is, we'll use our fancy butterfly brackets, x is in the set all reals. And this is where I'm going to be a stickler for notation here. I do want you to write it like this. Sorry, my first butterfly bracket got goofed, right? But you're going to use your butterfly brackets, and I don't just want you writing all reals anymore, right? That's not good enough anymore. I want to see good notation here, okay? So x lies within the set all real numbers, okay? Range, same idea, butterfly brackets, okay? And that's the same thing, right? You can see that it's going on and on forever in a vertical direction as well. So y is also in the set of all real numbers, okay? It can be anything. Is this increasing or decreasing? So as you read your graph from left to right, what you're asking is it going up or is it going down? Well, hopefully you say, well, as we read from left to right, this is going up. It's trending in an upward direction. So this is increasing. And if you think about a line, is there any maximum or minimum point? No. So neither of those are the case. Later down the road, we'll talk about, well, if there's no maximum, what that really means is its maximum is infinity and its minimum is negative infinity. For now, just put not available, but it's something to be familiar with. Okay, so those are linear functions. Horizontal and vertical lines are other forms of linear functions. They're kind of special cases, if you will, right? But the domain of this line here, right, the domain is still x's in all reals, right? You can see that it's covering all your x's, right? The range in this particular case, we only have one y value. So we would say, well, the range, I'm sorry, is just 2. The range is just 2. Is this increasing or decreasing? Neither. This is constant. It's not going up or down. And there's no maximum or minimum. Over here, now in this case, the domain looks a little bit different, right? The domain in this case, and this is why it's not a function, right? This is not a function. It does not pass the vertical line test, but you can see all of your x values are 4, and they all go to a different y value. Your range, however, in this case, now your range is that y is in all real numbers. Okay, is this increasing or decreasing? Well, again, it seems like maybe it's increasing, but there's really no ability to read this from left to right. So this is also, it doesn't really apply, right? Because it's not a function, right? And then again, same idea, no maximum or minimum here. Okay, now let's move on to a totally different family. And I'm going to speed this up for the sake of, we've got a good amount of content to get through, and I don't want this to be an hour-long video. Sip a little LaCroix, and here we go. So now we're talking about absolute value functions, right? You can see f of x equals the absolute value of x is the most basic as it gets. This is its most basic graph here. And the domain of this, if you look, hopefully you recognize, well, again, all of your x's are covered. As you go from left to right, your x's are non-restricted, so x is in all real numbers. And y in this case, okay, y in this case, there's a special way we're going to write this. The way we say this is that y is in all real numbers, and this is how you write it pretty much every time unless you're just listing values, right? So if you look at this one, we just listed that the range was just 2. There was one y value, so we just list that it's 2. Okay, in this case, we need to say that y is in all real numbers, then we have this vertical bar here. That vertical bar means such that y is what? Well, where do our y values start? So I read this from bottom to top. So down here, we got nothing, nothing, nothing. Our y values start at 0 and then keep going up. So y is greater than or equal to 0, right? All of your y values on this graph are greater than or equal to 0. Okay, is this increasing or decreasing? Well, hopefully you look and say, well, it's increasing over here. It's increasing when x is greater than 0. Okay, it's decreasing over here, right? It's decreasing when x is less than 0. So it's increasing when x is positive. It's decreasing when x is negative. There is no maximum on this one. However, hopefully you look at this one, while it comes to this little peak at the bottom, right? That means our minimum, this should be marked with a point. Our minimum is at the point here, 0, 0. That is our minimum point. And that is the gist of an absolute value. It looks kind of like a V. Quadratic. This is going to be an important one for down the road. Anytime you see an x squared in an equation, that's going to be your cue that this is a quadratic, and it creates this lovely little U shape that we call a parabola. Okay, it creates this lovely U shape that we call a parabola. Okay, the domain of this is still totally unrestricted. X can still be any old number we want it to. X can still be any old number we want it to. So X is in the set of all reals. And this hopefully will remind you of your absolute value one. Notice it comes to this nice little peak here. We have no y values below 0, right? There's nothing here. And then starting at 0, we start to have y values. So we say y is in the set all reals such that y is greater than or equal to 0, right? Your y values start at 0 and continue upwards. This is, again, very similar to the absolute value graph if we're comparing these. Notice it's increasing when x is positive or when x is greater than 0, and it's decreasing when x is negative or when x is less than 0. Okay, again, no maximum point, right? There's no top of this graph here, but there is a bottom, if you will, a minimum point. That point would again be 0, 0. So a lot of similarities between the quadratic and the absolute value. The absolute value ends up looking a little more like a V. The quadratic is a little bit more like a U. Now we've got all these different polynomials. So we just talked about the quadratic here, so we're not going to remark those. And we're going to go through these next ones. We're going to forget the increasing, decreasing, minimum, maximum for these, right? Because that's not terribly important. But I do want to discuss the domain and range of these. Okay, so the domain and range for each of these. Again, the domain is generally speaking unrestricted, right? You can plug anything in for x. So for all of these, the domain is going to be the same. X is in all real numbers. Okay, x is in all real numbers. Okay, now the range might differ. Well, in this particular one, the cubic, okay, so notice all of our y's are covered, right? As we go across, right, we've got all sorts of y's here. It does go all the way down. It goes all the way up as well. So this one, y is in all reals, right? We have all of our y values covered. In this next one, well, this one looks a little similar to your parabola, right? Notice it has a start to its y value. So again, there's nothing down here y values wise. Your y values start at 0, 0 and continue up. Ooh, I'm gonna say, bless me, thank you. You're welcome. The range for this one would be y is in all real numbers, and again, such that y is greater than or equal to 0. That's a common pattern hopefully we're seeing. And last but not least, again, if you look at this one, the range, your y values, well, they're everything. Y is in all real numbers. Okay, so these are your different polynomial functions, right? Quadratic, we just talked about, that's x squared. Cubic is x cubed, and it looks kind of like this, almost like if you turned this piece of the parabola downwards, like you almost reflected a little bit. It's actually exactly what it looks like. Quartic, it's like a parabola but thinner, and then quintic, it's like a cubic but thinner. But these are just, as you tack on more and more x's, this is what your graphs look like. Rational functions, okay? So a rational function, rational, remember, is a ratio, is a fancy word for fraction. So your rational functions naturally have a fraction of them. It's what happens when your x is in the denominator, okay? And these ones are a little funky. These are a little funky. You actually have two pieces to your graph here, and they're what are called asymptotes. Asymptotes, or as I like to call them, a donkey in a bag. You'll get that joke one day, right? But there are these imaginary lines on your graph. See this imaginary red line, and there's an imaginary line here, and your graph is going to get closer and closer and closer and closer to those, but never actually touch it. Again, we'll discuss this a little bit later on in the year when we actually talk about rational functions, but it's a good concept to know right now. So this one, your domain, is that x is in all real numbers. But if you have this imaginary line here, your graph is never going to touch that imaginary red line. So we're actually leaving out 0. So x is in all real numbers such that x does not equal 0, which makes sense if you think about it based on the parent function. Remember this idea of restrictions, right? Well, we're not supposed to divide by 0, so it makes sense that if we're talking about 1 over x, x should not equal 0. It's that same idea. For the range, it's the same idea. Y is in all real numbers such that y does not equal 0 again, and that's because of this imaginary line here. We're going to get closer and closer and closer and closer to it, but we're never actually going to touch it. We're never going to achieve 0. Okay? So increasing, decreasing. This one's a little bit funny, but if you look at it as you read from left to right, we're decreasing here. And even though we go up here, we're actually still decreasing here, right? So this is constantly decreasing, and there is no maximum or minimum. No maximum or minimum. Okay, we're getting close. We got square roots and exponential functions, and that's it before we just wrap up the last few things here. I know this feels like a lot of notes, but again, that's why I wanted you to make sure to have the packet. Square root function. So this is one where you have a square root around your x. Okay, domain here. This is another one with an interesting domain. Notice, where does your graph start? Well, it starts at 0, and that makes sense. So we're going to say x is in the set of all real numbers such that x is greater than or equal to 0. And that makes sense graphically, right? If you just look at your graph, where do your x values start? Well, they start at 0. Okay, that also makes sense here because if you've got the square root of something, we know you can't take the square root of a negative number. So it makes sense that whatever you plug in for x has to be positive or 0. So that's how we get that piece there. And same idea here, y is in all reals such that, and again, if you look, your y values also start at 0. So y is greater than or equal to 0, right? Your square root's not going to spit out a negative number either. Okay, is this increasing or decreasing? Well, as you read it from left to right, this is increasing. And then there actually is both a maximum and a minimum, and there actually, or I'm sorry, there's no maximum, right? Because it's going to keep getting bigger and bigger, but there is a minimum. That minimum would be 0, 0. That is the lowest point on this graph. Last parent function are the exponential functions. That means you have an x in your exponent there, which is a little goofy looking, but it's the real deal. Okay, so your graph looks like this. It's this constantly increasing guy here. And so your domain, well, is there anything you can't plug in for x? No, x can be anything. And if you look at your graph, that works. So x is just in all reals. The key with exponents is no matter what you plug in for x, you're actually never going to get a negative number. And if you look, that makes sense. There's another one of these asymptotes is what they're called, right? And if you look, your graph is going to keep getting closer and closer and closer and closer and closer to that, but it's never actually going to touch it. So we're going to say here that y is in all real numbers such that y is greater than 0, right? It's never going to end up being 0. Okay, hopefully you look at this and you say, well, that's constantly increasing, Mr. Kaplan. As I read this from left to right, there is no maximum or minimum. There is no maximum or minimum. And that's that. So those, again, this was a lot of information. And the goal here, again, I'm not going to sit here and ask you specifically, well, what is the minimum of a typical quadratic parent function, whatever. That's not what I'm going to do here. I'm looking for familiarity. So I know it was a lot. I know it feels a little daunting to have all these parent functions, but again, I'm looking for familiarity. I'm looking so that later on down the road, when we're talking more about graphing, you have the gist of this. Even though we're not talking about it a ton this chapter, I just want you to have the basics of it, okay? So these last couple of things we're talking about is, well, what if I want you to tell me the domain based on a given function, like written out, not graphically. Okay, so functions can be defined by an equation without a specified domain. It is important to know the domain of the functions that we know the values of the function is possible. When finding the domain of the function given an equation, we want to name the set of real numbers for which the equation produces real numbers. Okay, so we want to list the numbers that we're allowed to plug in, essentially, is what we're saying. Okay, the two main things that we can't have. Okay, the two main things that we can't have, and hopefully you recognize a couple of these situations in this. But one, you can't divide by 0. Okay, you can't divide by 0. You can't have 0 in the denominator. Okay, the other thing that you can't have is you can't take the square root of a negative. Okay, you can't take the square root of a negative. So those are the two things we want to keep our eyes out for. So when we're listing our domains here, right, we want to make sure that we're not dividing by a negative, right, and we're not taking the square, we're not dividing by 0, and we're not taking the square root of a negative number. Okay, so this first one, okay, whenever I have a variable in the denominator, whenever I have an x in the denominator, I'm basically going to say, well, I know that that entire denominator can't equal 0. So x squared plus 4 cannot equal 0. And this is kind of a goofy one to start with, but you essentially want to solve that equation. You say, well, x squared, if I subtract 4, we get x squared equals negative 4. And if you remember this from algebra 1, you'd square root both sides. And this is one that would actually give you no solution, right? Because you can't square root a negative, just like we said. But what that means for our domain, well, there's actually nothing you can plug in for x, because think about it. Whatever you plug in, you're going to square it to make it positive, and then you're going to add 4. So it's just not possible that you're going to get 0 there. So this domain actually, the way we write this is D for domain equals, fancy brackets, x is in all real numbers. There you go. Okay, because we got no solution, that means there's nothing we can plug in for x that would make our denominator equal to 0. So x is in all real numbers. All right, this one, again in our denominator, x times x plus 2 cannot equal 0. And if you at least vaguely remember factoring, hopefully you say, okay, well, I remember that this basically means, well, either x doesn't equal 0, well, that's one solution, or x plus 2 does not equal 0, right? And if you solve that, you subtract 2 to say, well, x does not equal negative 2. And those are the two things that x cannot equal here, right? So we say, for our domain equals, fancy brackets, right? X is in all reals such that x does not equal 0 or negative 2. Okay, so x is in all reals such that it does not equal 0 or negative 2. And there you go. Okay, so those are the two things that x can't equal or we divide by 0. All right, this is where we come into what we did last unit with solving some inequalities, because we want to make sure that what's under our square root here is not negative. Well, how do you say something's not negative? Well, that means our 2 minus x has to be not negative or greater than or equal to 0. How about that? Okay, so you're going to subtract 2. So negative x is going to be greater than or equal to negative 2. And then when you divide by negative 1, this last step, don't forget to flip your sign. So we get x is less than or equal to negative 2 divided by negative 1 is positive 2. So in order for this one to work, x has to be less than or equal to positive 2. So our domain then, d equals, fancy butterfly brackets, x is in all reals such that x is less than or equal to 2. Okay, so when you have a denominator, you set it so that it does not equal 0. When you have a square root, you set it so that it's greater than or equal to 0. Okay, so in this particular one, we kind of have a double situation. So in this one, we've got, well, let me zoom in a little bit here so we have a little more space. It is both in the denominator and a square root. Well, normally we'd say that 4 minus 3x has to be greater than or equal to 0. But do we actually want it to equal 0? No. So that 4 minus 3x just has to be greater than 0, okay? So it's got to be greater than or equal to 0 because it's a square root. And then it ends up being just greater than 0 because, well, we don't want our denominator to be 0 either. So this is kind of a twofold situation. So when you have a radical in the denominator, instead of greater than or equal to 0 like we did over here, it's just greater than 0 because it's got to fit both of these criteria. You can't divide by 0 or square root of negative. So subtract the 4, you get negative 3x is greater than negative 4. Divide by the negative 3. Don't forget to flip your sign. So x is less than positive 4/3. Okay, so again, we write that as, well, your domain then is x is in all reals such that x is less than 4/3. There you go. Getting close, getting close. So this one, well, we don't have a denominator. We don't have a square root. So in this particular case, your domain is just all real numbers, right? Domain is that, fancy brackets, x is in all real. So again, don't overthink it. The only things that are ever going to limit your domain are a denominator or a square root. Well, this next one has both. Okay, so what we know is the denominator can't equal 0, so n squared plus 3n cannot equal 0. And what we have in the numerator, the n plus 3 under the radical, well, under a radical, it's got to be positive. So n plus 3 has to be greater than or equal to 0. So this kind of shows you both scenarios here. Well, for those of you who have forgotten how to solve something with a squared in it, this is something where you want to factor. Okay, so we basically want to pull an n out of this, right? We're undistributing an n. So we get n times, well, n times what gives me n squared? N times n gives me n squared. Plus n times what gives me 3n? N times 3 would give me 3n. So n times n plus 3 cannot equal 0. And hopefully now you're saying, oh, well, this looks just like number 2 up here. Okay, this gives me that n cannot equal 0. And this gives me that n plus 3 cannot equal 0, which means if you solve that, n cannot equal negative 3. Over here, you subtract the 3, and we say, well, n is greater than or equal to -3. So here's the deal, and this is a tough concept, but if you get this, you should be feeling in good shape. Now we kind of have to combine this. D equals fancy brackets. X is in the set of all real numbers such that, okay, n cannot equal 0. That doesn't change. However, we've got two things with -3. We say that n is greater than or equal to -3, but we also say that n can't equal -3. So those kind of offset each other in that, well, it can't be greater than or equal to it if it can't equal to it. So what we have is we take away the or equal to, and n is just greater than -3. If you followed that, awesome. If you didn't, we'll work on it, but that is the idea here. Okay, so if you're just given the written out mathematical form of a function, this is how you can still tell what the domain is. Again, the two things we're looking for are denominators. We don't want to divide by 0, and square roots. We don't want to take the square root of a negative. Okay, last little bit here. Whew. Last little bit, we just want to say the domain and range, so D equals and R equals, of each of these graphs. So I'm going to write it out here. D equals R equals. And this is our last thing. I know this was long. I know this was a good bit of notes here, but there's a reason for that. We're going to wrap it up already next time. Okay, so the domain here, well, this one's not continuous. This is just straight up points. So if you list out your points here, you have the point. Well, that would be 1, 5. The point 3, this one is 3, 5. This one here is 4, 2. And this one here would be 6, -2. Hopefully remember how to find ordered pairs. Well, your domain again, in something like this, it's just listing your x value. So 1, 3, 4, and 6. Your range here is just listing your y values. Again, go from least to greatest, so that'd be -2, 2, and 5. You don't and should not list that 5 twice. It's just listed once. And there's your domain and range for this one. Now the rest of these are continuous, right? So this one's a parabola. So your domain should match the parent function, okay? The idea is there's nothing you can't plug in for x here. If you think about it, this is going to involve something with an x squared. So x is just all real numbers, okay? It's going to continue forever and ever in this direction, even though you can't see that specifically on the graph. It does happen. X is all real numbers. Your range, on the other hand, well, this is one where we say, well, y isn't all real numbers such that, well, where do our y values begin, right? So if we're going from the bottom, well, we've got y values, got y values, got y values. Ooh, stop. Our y values cap right here. So that means, well, if you look at this, your y values are all less than or equal to 4. Okay, your y values are less than or equal to 4. Okay, this is just a straight linear. It goes on forever and ever in both directions, both your x values and your y values. So this one's nice and easy. X is in the set of all reals, and y is in the set of all reals. Okay, and then this last one, this one's a little goofy looking, right? This isn't going to come from a function like a parent function, right? But hopefully just by looking at this, you can tell, okay, well, I've got all my x values covered, right? It looks like it keeps going to the left, and it looks like it keeps going to the right. So that's what we'll accept that. So x is going to be all reals. And if you look, let's find our lowest y value. Well, it looks like our y values cap here at -4, right? And it looks like we've got everything above that. Okay, it looks like we've got everything above -4. So we're going to say y is in all reals such that y is greater than or equal to -4. We'll circle our answers here. Sorry, I forgot to circle these ones. And that's that. We got to work on domain and range. They're two very important concepts, not only for the rest of this class, but moving through your math career here, you're going to talk about domain and range a lot. Okay, so yes, I am going to be a stickler on notation. Make sure you've got those correct brackets there. They don't need to be perfect, right? You can tell many of mine aren't perfect, but I should tell that that's what you were going for. And then all of them like this, right? You've got x is in the set, that fancy little e there, all real numbers. Let's make sure our function notation and our set notation is really on point here, okay? This was a lot, like I said. The main things are familiarity with these family functions, how to tell whether or not something is a function, and then domain and range, okay? Both coming from graphs, like we did down here, or just domain coming from functions, like we did up here, okay? Take some time on the homework. I know this was already long notes. The homework shouldn't take you too terribly long, but take your time on that. This is important stuff, guys, and we don't have that much time to pick up the pieces here because it is such a quick unit. So really take your time on this. If you have questions, let me know. And with that, thank you all so much and take care. Nice